next speaker is Nicholas Williams, and the title of his talk is "The First Higher Stashev-Tamari Orders Are Quotients of the Higher Bruchal Orders." So go ahead.
Thanks. Let me just share my slides and put them in the chat as well. Okay, so hopefully everyone can see that now.
Yeah, we can see them.
And let me just put them in the chat. Sorry. Just a second. Cool. Great. So thank you very much to the organizers for putting on this conference, particularly in such difficult circumstances. So today I'm going to talk about a paper which I put on the archive about a year ago, about kind of certain partial orders and the relationships between them. So two particular partial orders I'm talking about today are the first higher Stashev-Tamari orders and the higher Bruchal orders. If you haven't heard of these, essentially the first higher Stashev-Tamari orders are in some sense a higher dimensional version of the Tamari lattice, and the higher Bruchal orders are in some sense a higher dimensional version of the weak Bruchal order on the symmetric group. So the motivation essentially comes from this paper of Demakis and Müller-Heusen, which appeared in the Tamari Festschrift. And essentially they study a class of KP solitons. So these are essentially solitary waves designed by a certain differential equation, and kind of inspired by the combinatorics of these sort of wave solutions, they define a certain quotient of the higher Bruchal orders, which they call the higher Tamari orders. And they conjecture that actually these orders they define are the same as these previously existing first higher Stashev-Tamari orders. And the upshot of my paper is to prove that this conjecture is true. Okay, so what are these higher Bruchal orders? Well, they're defined as follows. It takes a kind of few steps to define them. So firstly, if we take a subset of the integers from 1 to n of size delta plus 2, called A, then the packet of A is the set of subsets of A of size delta plus 1. So if A is just a set 1, 2, 3, then the packet of A is the set consisting of 1, 2, 1, 3, and 2, 3. And the packet of A is naturally ordered lexicographically. So again, if we take 1, 2, 3, then the lexicographic order is 1, 2, then 1, 3, then 2, 3. And okay, we can then use this to define this key notion, which is an admissible order of the set of subsets of the integers from 1 to n of size delta plus 1. This is a total order where every packet is either ordered lexicographically or reverse lexicographically. We then define a certain equivalence relation on admissible orders. So we consider two admissible orders to be equivalent if one can get from one to the other by changing the orders of elements that are adjacent and do not lie in a common packet. So for instance, 2, 3 and 1, 4 can't lie in a common packet because their union is of size 4. So if we had an admissible order which had 2, 3 and 1, 4 next to each other, then we could switch the order and still preserve the equivalence class. Okay, then having done this, we can define the inversion set of an admissible order, and that's the set of subsets delta plus 2, which are ordered reverse lexicographically. Finally, with all these ingredients, we can define the higher Bruchal order Bn delta plus 1. These were originally introduced by Manin and Schechtman. So the elements of this partial order are equivalence classes of admissible orders on the set of integers from 1 to n of size delta plus 1. And the covering relations of the order are just given by adding an element to the inversion set. So I'll do an example of this on the next couple of slides, because I think that this is quite a complicated definition. It's worth dwelling on just exactly how this generalizes the weak Bruhat order on the symmetric group. So for delta equals 0, packets are just of size 2, so they're always ordered lexicographically or reverse lexicographically. So all total orders are admissible. And moreover, the elements of the admissible order are of size 1, so each pair of elements does occur in a common packet, so there's no equivalence relation, or rather the equivalence relation is just of the discrete equivalence relation. So if we have Bn1, then the elements are just all of the total orders of the integers from 1 to n, which are just elements of the symmetric group. And then the inversion sets are just inversions in the usual sense. They're pairs of elements whose order is exchanged by the permutation. And yes, the covering relations of the order are permutations which increase the number of inversions by 1. Okay, just to briefly look at an example which is not the weak order. So here's the different equivalence classes of admissible orders for the higher Bruhat orders B42. So we're ordering subsets of the integers from 1 to 4 of size 2. The minimal element 0 hat here is of course just the lexicographic order on everything, and the maximal element is just the reverse lexicographic order on everything. So we're going to have the alpha 1 covers 0 hat here, and one can see that because essentially to get from 0 hat to alpha 1, you exchange 1, 4, and 2, 3, which don't lie in a common packet, so that preserves the equivalence. And then we invert the packet, which consists of 1, 2, 1, 3, 2, 3, so that the order changes to 2, 3, 1, 3, 1, 2. If we were to compute all the inversion sets, then this is what we get. And so the Hasse diagram of the place set looks like this. Okay. So I'll briefly just talk about the work of Demakis and Müller-Huijsen and kind of try to vaguely motivate their definition of the higher Tamari orders. So it starts with the KP equation, which is a differential equation describing solitary waves known as solitons. You can approximate solutions to the KP equation with certain tropical varieties. So these are the locus where the maximum of a set of particular affine linear functions, which I'm going to call phases, is achieved by at least 2 of the functions. So obviously at all points, some function will be maximal in the set, and the points where that maximum is actually achieved by not just 1 function, but 2 functions is going to be the tropical variety. And so Demakis and Müller-Huijsen only look at a particular subset of solutions to the KP equation, which have a particular combinatorial structure. So here's a kind of picture of what these solitons look like. So the things with, this is from their paper, the portions of the plot here with triple lines are the solitons. In the background, we have this hyperplane arrangement, which is the rest of the plot, the bit which is not tripled. So the idea here is that for the maximum of the set of phases to be achieved by 2 of them, then in particular those 2 phases have to be equal at that point. So if we just plot the points where a pair of phases are equal, because these are affine linear functions, this is going to give us some hyperplane arrangement. And then the way they think about this is that certain parts of the hyperplane arrangement are going to be visible as in give a part of the soliton plot when the equal phases are not just equal to each other, but actually maximal. And what they show, which I'm not going to explain, but essentially the different hyperplane arrangements that occur here encode elements of the higher Bruchart orders. So the natural question is, well, we're not necessarily interested in the hyperplane arrangement, but the sort of visible bits of the hyperplane arrangement, which correspond to these soliton plots. So what combinatorially do those correspond to? And the other they come up with is these higher Tamari orders, which are defined in terms of the higher Bruchart orders. So if we let alpha be an admissible order of the integers from 1 to n of size subsets of size delta plus 1, and we let I be such a subset, then if we take an element k outside I, we say that I is invisible in the packet I union k if either I union k is not inverted by alpha and the number of elements of I greater than k is odd, and or alternatively, kind of the opposite is true. I union k is inverted and the number of elements of I greater than k is even. And we say that the subset I is invisible in alpha if there's some packet in which it's invisible. And if there's no packet in which it's invisible, then we say that I is visible in alpha. And the idea is that this somehow gives the criterion for the visible parts of the hyperplane arrangement. Okay, if we let V alpha denote the elements of the set of subsets of integers from 1 to n of size delta plus 1, which are visible in alpha, then the higher Tamari order T n delta plus 1 has elements, sets of visible elements of admissible orders. And we have V alpha less than or equal to V alpha prime if and only if the equivalence class of alpha is less than the equivalence class of alpha prime in the higher Bruchart orders. So to see two different admissible orders, or even two non-equivalent admissible orders might have the same set of visible elements. So you can think of, so this is really a quotient of the higher Bruchart orders. If you think carefully, it's not actually immediately obvious that this is well defined, because it's not actually obvious that this is a transitive relation. The results we're going to see later, of course, will imply that it's well defined. So that's just a remark. So okay, this is the higher Tamari order. So let's look at an example. So I'm not going to go through showing exactly why these are the visible elements, but if we take these admissible orders from B42, which we had earlier, then these are their sets of visible elements. So you can see that some different non-equivalent admissible orders do get identified by this quotient. And the post set we obtain looks like this. But again, I haven't defined these first highest Tamari orders yet, and the definition of these looks really quite different. So this is defined really a bit more geometrically in terms of cyclic polytopes. So the cyclic polytope Cn delta is the convex hull of a choice of n points on the curve with coordinates t squared up to t to the delta. The facets of this polytope come in two different types. So we have upper facets, which are the ones that can be seen from a sort of large positive delta coordinate, and the lower facets are the other ones. there's a natural projection map from the delta dimensional cyclic polytope to the delta -1 dimensional cyclic polytope, given by forgetting the last coordinate. And if we take the upper facets or the lower facets of Cn delta, then these give us a triangulation of Cn delta -1, and these are known as the upper or lower triangulation. If we take a cyclic polytope which is sufficiently small, so if it has delta +2 vertices and delta dimensions, then it will only have two triangulations, namely the upper triangulation and the lower triangulation. So for instance, for delta equals 2 here, we just have quadrilateral, and that has two triangulations given by the choice of diagonal, and those correspond to the upper and lower facets of C43, which is just a simplex. So yeah, so a simplex has 4 facets, and the way C43 lies, 2 of those facets will be on one side and the other 2 facets will be on the other side, and these give us 2 different triangulations of a quadrilateral. We can use this observation to define this increasing bistellar flip operation on triangulations. So we take a triangulation T of Cn delta, and we look for a small copy, well, for a copy of C delta +2D within it, which is triangulated by its lower triangulation. And within that small copy, we replace the triangulation by the upper triangulation to obtain a new triangulation T prime. And in this case, we call T prime an increasing bistellar flip of T. So in terms of quadrilaterals, this is just flipping a diagonal inside a quadrilateral in a certain direction. But this is the generalization of that operation to all dimensions. The first highest Stashev-Tamari order, which is originally introduced by Kapranov and Voevodsky, but this definition is really due to Edelman and Reiner. This is the pose set on triangulations of the cyclic polytope Cn delta with covering relations given by increasing bistellar flips. So first of all, this immediately doesn't really look anything much like the higher Tamari order we just saw. The objects are completely different, or so it seems. But in order to connect them, there's a slightly different way of defining the higher Bruhat orders, which kind of will make the connection between the two more apparent. So one can define the higher Bruhat orders in terms of what's called cubulages of cyclic zonotopes. So these are also called fine zonotopal tilings in the literature. So take a curve which is quite similar to the curve we had before, except instead of being t squared up to t to the delta, it's 1 t squared all the way up to t to the delta. And instead of taking the convex hull of various line segments, of all the points, we take line segments and then take their Minkowski sum. A cubulage of the cyclic zonotope is a tiling of it by parallelotopes, so just kind of high dimensional parallelograms, which we often refer to as cubes. So this is kind of instead of a triangulation, this is what we do. You can similarly define upper and lower facets of the zonotope, and these give upper and lower cubulages. If we take a zonotope sufficiently small, so with delta +2 line segments in delta +1 dimensions, this only has 2 cubulages, the upper and lower cubulage. And so we can likewise use this to define a flip operation by looking at a small subzonotope in the cubulage and replacing the cubulage with the upper cubulage if it has the lower cubulage. And it turns out the higher Bruhat order can also be defined as the pose set of cubulages on the cyclic zonotope with covering relations given by these increasing flips. And this is also originally due to Kapranov and Voevodsky, but Hugh Thomas kind of gave the details of this. So here's an example. Here's a cuboid of Z42. You can label the cubes of the cuboid in a natural way by subsets of the integers from 1 to 4 of size 2. And I won't explain exactly how, but you can imagine that you can actually read off an admissible order from this, and this is how this corresponds to the original definition. Okay, what does visibility mean in terms of cuboids? But you can show that actually, so in terms of admissible orders, it's subsets which are visible. As I just said, these correspond to cubes of the cuboid. One can show that a cube of the cuboid is visible if and only if it touches the origin. It's quite straightforward to see from the definitions that the cyclic polytope is the intersection of the cyclic zonotope with the hyperplane at x1 equals 1, if you just think of the two different curves we use. And this means that if you take all the visible cubes of the cuboid, this actually gives you a triangulation of the cyclic polytope. So if you intersect one of these cubes with the hyperplane at x1 equals 1, then you get a simplex. So this collection of cubes turns into a triangulation. And so taking the visible elements of the cuboid gives us a certain order-preserving map from the higher Bruhat orders to the first higher Stashev-Tamari orders. And the definition of the higher Tamari orders essentially amounts to it being the image of this map. So the elements, the things which are triangulations which come from the visible cubes of the cuboid, and the relations in this order are the relations that come from the relations in the higher Bruhat orders. So here's an example. We take this cuboid, we intersect with the hyperplane at x1 equals 1, and we obtain this sort of triangulation of a one-dimensional cyclic polytope. In 2 dimensions, well, to give 2-dimensional triangulations, it's like so. So this is a 3-dimensional cuboid. We intersect with the x1 equals 1 hyperplane. We obtain the following triangulation. So the conjecture that the highest Tamari orders, the same as the highest Stashev-Tamari orders, is equivalent to this map V being surjective and full, so that all of the elements are the same and all of the relations are the same. The surjectivity of the map was actually already known from work of Rambau and Santos, who put this all in a slightly different framework, which is more in the language of matroids. But we provide a new construction to prove surjectivity. And moreover, our construction actually allows us to show that the map is also full, so that every relation in the higher Tamari orders actually comes from a relation in the higher Stashev-Tamari orders. And so we have our main theorem that these two partial orders are in fact the same as conjectured. So thank you very much for listening. That's the end of the talk.
Thank you very much. Do we have questions for Nick?
Just checking, was the we official, or you actually have a collaborator?
So yeah, no, it's there's no collaboration. Yeah, it's the royal we.
I have a small question.
Yes.
If you have triangulation of the cyclic polytopes, then there is many cubillages which can be lifted.
Yes. Yeah.
And then you draw a picture at the beginning which related to KP equation. Then somehow you emphasize that there is a hyperplane arrangement. And yes. Then the question, is it possible? So, and if we have cubillages, then some cubillages correspond to hyperplane arrangement and some not. And is it true or not? So if we have triangulation of the cyclic polytope, then it could be lifted to the cubillage which correspond to some hyperplane arrangement.
Yes. That's a good question. It's not true actually. So when these authors write this paper, they don't kind of acknowledge the fact really that it's only the regular cubillages that actually give you hyperplane arrangements, as you say, and there are some ones which are not regular, which don't give you hyperplane arrangements. And it's the same with triangulations of cyclic polytotes. So it's only the regular ones which will correspond to solitons. And so if you have a non-regular triangulation, then you won't be able to lift it to a cuboid, which gives you a hyperplane arrangement, because otherwise the triangulation would have to be regular.
But for regular triangulation, it's possible to lift.
Yes. Well, it is. It should. Yeah. No, I'm pretty sure it is possible, because if you have a regular triangulation which is defined by certain weights, then you use those same weights to define a regular cuboid. So I think they lift quite straightforwardly. Yeah.
Thank you.
Thanks.
There's the question in the chat. Vincent is asking what properties are known for these posets.
Good question. So it was originally conjectured that for the first highest staff Tamari orders, it was originally conjectured that these were always lattices. That's known not to be true in general, but it's true. It's known to be true in dimension up to 3. For the higher Bruja orders, for dimension 1, where it's the weak order on the symmetric group, that's a lattice, but in higher dimensions, it's not a lattice. In general, a lot of the properties aren't that nice. So obviously the Tamari lattice has a regularity property, and these first highest dash Tamari orders are in general not regular. The higher Bruja orders might be regular, but I can't remember. Yeah.
No.
Yeah, they had. Generally, the property is not that nice. So Gleb is trying to say something. Yeah.
No, not like this. Yeah.
Yeah, they're not lattices. Yeah. But for low dimensions, they are. Yeah.
Okay, so let's thank Nick again. Thanks so much.